AI is a big field, and it's improving every day. There's decision trees, Monte Carlo search, SAT solvers, deep neural networks, and a whole bunch besides. And in recent years, I'm sure we've all been blown away by what these machines are capable of. Unfortunately, this explosion in AI research has so far had a limited effect on video games, and I think there's 3 key reasons for this. First off, these techniques are really complicated. If you're a major tech company, then you can afford to hire a team of ML researchers to teach your bots to tell a cat from a rat or a bat. But game developers are usually under tight money and time constraints, and they need something that just works straight up. On top of that, many AI techniques are slow and need racks of cloud computers to run well. In a real-time video game where every millisecond matters, this is a killer. And finally, these techniques are actually overkill for most games, because it turns out that there are far simpler ways to create something that seems intelligent, in a video game setting at least, without actually being very smart at all. And in this video, I'll be breaking down one possible way that you could make such an AI. So, I've set up this debug mode in my roguelike game Patch Quest, just so that we can try out the concepts I'll be talking about. This monster here has had all of its AI stripped away, meaning it will happily stand motionless for all of eternity. The first major task is to let him move around. This monster does already have the ability to walk, but what it doesn't have is any concept of where it should walk. And that's going to be our task for this section, looking at the current environment and then transforming that into a single 3D vector that indicates which direction the monster intends to move. In Patch Quest, I do this using a system of virtual springs. Every nearby object can either push or pull the character using a spring, and we then add up all these springs to get the final movement intention. To show this in action, I'm going to add a spring that makes the monster follow the player. The colour of the spring shows its strength here. Green indicates a strong, positive force. Now, I'm going to throw in a few obstacles. These work the same way, except that they're inverted and they push the monster away when it wanders too close. This is drawn in red. This technique is very versatile. You can stop monsters from bunching together too much by adding repulsive springs between them. Or you can make a monster run towards a nearby power-up by adding an attractive spring between them. And the code that makes it all work is very simple too. You start with a 3D vector initialized to 0. We then loop through all the entities in the scene and calculate the push or pull strength for each one. The player spring pulls you towards a target distance. The obstacle springs work out the inverse cube of their distance and then push you away by that amount. This means that they push hard when you're up close, but don't push very much at all when you're far away. And the spreading out springs work the same way. To get our final direction, we just need to add all of these spring forces together. If the final vector is shorter than a threshold value, we discard it and just stay still. But otherwise, we normalize the vector and then return it. Normalize is a fancy mathematical word, but all it means is that we shorten the vector so that its length is exactly 1. Also, please note that all the code I'm showing in this video is pseudocode. You won't be able to drag and drop it directly into your Unity project, but hopefully it will be enough to show you how to get started making your own system. Okay, that's all we need to get our character moving around. I really like this technique because it's simple to set up, quick to run, and easily extendable. There is one caveat though. If your level contains concave shapes like this here room, then your characters can get stuck. That's because this technique is greedy and it moves directly towards the target without taking pathing into account. To fix this, you'll need to add pathfinding, but that's outside the scope of this video. However, once you have pathfinding, you can combine it with this springs technique pretty easily. Just instead of attaching a string that goes directly to the target, attach a spring that goes to the next node in the path you found. As for Patch Quest, the game never contains any such concave structures, which means that the greedy method works just fine. And I think this raises an interesting point. When you're dealing with a tricky AI problem, there's two major ways to solve it. Option 1 is to knuckle down and make some super smart solution. But option 2 is to redesign your game so that this tricky situation never turns up. By avoiding concave structures, I remove the need for my game to have any pathfinding at all. For another example, imagine you've made a top-down shooter with an enemy that can shoot bullets that bounce around walls. It's a cool ability, but it requires you to write an AI that can work out the angles for trick shots, which isn't trivial, especially if your bullet bounces multiple times. On the other hand, imagine you change this ability just slightly to making a weapon that shoots through walls. Mechanically, this is only a small tweak, but in terms of AI, it's huge. Instead of coming up with trick shots, the AI can now just shoot directly at the target without any concern for its surroundings at all. And so I definitely encourage people to take more of a big picture view of AI by designing games that don't require a lot of complex calculations in the first place. Speaking of shooting, it's high time we gave our monsters some attacks. Let's say this seahorse has 3 abilities. Bubble Wave and Water Wheel are both attacks, whereas Dash is a defensive move. Our goal here is to take a look at each ability and then convert them into a score between 0 and 1 that represents how useful the ability currently is. We can then just pick the ability with the highest score, assuming it passes a threshold value, of course. Attacks are very simple to work out. Each attack is given an optimal range. So, a shotgun style attack would have a smaller range and a rifle style attack would have a longer range. The closer the character is to this optimal range, the higher the ability's score will be. You can also throw in a check to make sure that you have direct line of sight to the target. Now, defending is slightly more complicated because it's reactive. You only want enemies to defend themselves if they're currently under attack. To work this out, we loop through all the bullets on the screen once per frame. If one of these bullets is heading straight for a monster, we then warn that monster, telling it a bullet is heading towards it from a particular direction. And this informs the monster that it can use its defense skill immediately. This code shows how the dash ability is evaluated. If the monster has been warned this frame, we tell it to dash in a perpendicular direction, at right angles to the bullet. Here you can see this visualized, with the yellow lines showing the warning vectors being projected out from the bullets. You can extend this approach to other actions pretty easily. For example, you could make a chase ability that becomes more desirable the further you are away from the player. Or you could add a melee ability that's only desirable when you are right next to the player. Regardless of how many abilities you add, the overall algorithm remains the same. Just convert each ability into a score for the current frame, and then choose the one with the best score. So the technique we just covered works pretty well, but it has one big problem. It's easy to accidentally set up your scores in a way that makes your character spam the same action over and over again. Let's take a look at a simple example. Imagine we have a monster with 2 close range abilities, Bite and Kick. They're both usable in the same situation when your distance is less than 1. But we gave Bite a slightly higher score than Kick. This means that Kick will actually never be used. What we really want is a character that tries to use its full range of moves, at least occasionally, while at the same time still taking into account the score of each move. That's a bit of a balancing act because those goals conflict, but there's a simple way through. What we need is a system of weights. where every time you use an ability, it becomes slightly heavier or less desirable. This way, even bad options will be used on rare occasions, when all of the better options have already been tried recently. To do this, I created this set of strategy types. In Patch Quest, the strategies are primary fire, secondary fire, defend and chase, plus a few other ones that aren't relevant for this video. This set will depend entirely on the kinds of actions your character can perform. We can then go back and update our action scoring system so that each action now has a strategy as well as a score. Easy. Okay, so here's where the magic happens. We create an array of weights for each of our strategy type. They're all set to 0 to begin with. To find the best action in a particular situation, we first evaluate every ability that this character can perform, converting them all into a score and a strategy. We then try to find the highest scoring option. Note here that we subtract the weight of an action's strategy from its score. Or in other words, a heavy strategy makes an action less desirable. Since our weights are all set to 0 to begin with, this has no effect at first. Once an action has been chosen, we increase the weight of its strategy, and we decrease the weight of all other strategies. This means future actions using that strategy will be comparatively less desirable. And finally, we decrease the weight of every strategy just a little bit each frame. This is just to help avoid deadlock situations wherein every strategy has become too undesirable to be performed. And that's it. This little system is all you need to give your characters the gift of decision making. They will try to use high-scoring abilities, but they'll also try to mix up their strategies and be a little bit unpredictable. It adds just that little bit of fuzziness into the mix that makes it hard to predict exactly what your character might do next. And for a video game, that's a great feature to have. It also means that your ability evaluation scores don't have to be exactly precise. They can just be a rough guide and the system will adapt to them. We can make some simple tweaks to the system to improve it further. For example, if we initialize each strategy weight to a random value, then every character will behave a bit differently right off the bat. We could also make some characters prefer some strategies over others. For example, an aggressive enemy could give a boost to the attacking strategies, whereas a tanky enemy could give a boost to the defending strategies. There's a bunch of ways to tweak and expand this system, and to be honest, that was really my whole intention. This isn't the most advanced AI system in the world, and it's not the smartest either, but it is pretty simple to set up and pretty flexible for what it is. So, let's summarize. These 4 bullet points should be all you need to get started making an AI for your game. 1. Use springs to make your character move towards its goal and away from hazards. Springs are an easy and extensible way to influence which way your character moves. They can push or pull, and their strength can vary depending on their length as well. 2. Convert each possible action into a score and then choose the best one. The tips I covered earlier should help you get started with this. Some actions may require a little creativity to calculate their score, but to be honest, you really just need to provide a rough score estimate because of the next point. 3. Weigh these scores to force your character to mix things up. By breaking up the actions into categories and weighing down each category as it gets used, you can make your AI try out the full variety of its moveset while still preferring the higher scoring options. And finally, a bonus point. Consider whether changing your game's mechanics can remove the need for complex AI in the first place. By avoiding any concave structures in my levels, I also avoided the need to add pathfinding. And there's bound to be a bunch of other situations where taking a step back and modifying your game's mechanics can save you a headache in the AI department. I hope you found this video useful, and I'll be back next month with some more game dev tips and tricks, so remember to subscribe and ring the bell if you want to see them. As for Patch Quest, I've been adding several new areas to the game, and I'll be showing them off at the end of the month. That's all for now. Thanks for watching.